So in this video, let's discuss multi-stage experiments. Now first, a multi-stage experiment is when we do several experiments and they're performed in a row. For example, we could roll a die, then spin a spinner. Now, how we do those events can affect whether they're independent of one another or dependent of one another. In an independent events, no event in that experiment influences the possible outcomes of the other event. For example, if I roll the die and then I spin this spinner, the die has no impact on how that spinner is spun. So those are considered independent events. Whereas dependent events are one in which what I did first will influence what happens second. And what you'll see, if you think about like cards, if I hand out cards, what I have left in my deck is dependent upon what's already been handed out. So the way we write this is you'll see this P and then in parentheses B with this vertical line A, and that means the probability of event B occurring given that A has already occurred. So we take into account that something has happened and that's dependent upon what just happened. So say, for example, I have a bag full of 10 colored marbles. I pull one out to see its color, but I keep it out. I keep it in my hand. That bag now has 9 marbles, which changes the probability for each of the other colors left in the bag. So let's look at a few things to help us out here. So one thing we can use is our fundamental counting principle of independent events to help us. And what this means is that if one event can occur m ways and the second n ways, then the total number of events is m times n. And this tells us our sample space. And a great way to figure out that sample space is using a tree diagram. So let's go back to our die and our spinner. So if I roll a die, I have 6 options. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. And with this spinner, I have 3 options. I could be red, green, or yellow. So each of these outcomes has the option of them being red, green, or yellow. Now I can look and say, well, how many total outcomes do I have? And if I count the 1 red, 1 green, 1 yellow, 2 red, green, yellow, keep going, there's 18 total. Well, I could also have said that's 6 options for the first event and 3 options for the second. 6 times 3 is 18. And if I want to look at my whole sample space, as I was just saying, 1 red, 1 green, 1 yellow, and you can keep going for each of those. Now say I want to calculate the probability of an independent event. So that means that I have the probability that event A occurs and event B occurs. Since they're independent, I can take the probability of each event individually and multiply it together. So for example, let's go back to our sample space we just had. The probability of rolling a 3 and landing on green. Well, the probability of landing on 3 is 1/6. And then I want to multiply that by the probability of landing on green, which is 1/3. And if I multiply 1/6 times 1/3, I get 1/18. Now what would that look like if I'd used my tree diagram? Well, we created the tree diagram a minute ago, and you can see, well, let's start here. Probability of 3 is right here, and the probability of green is right here, and that's the only way it happens. That's only one option out of the 18 total. So I was able to find them using the tree diagram or using our rule about how probability of independent events can occur. Now say that the second event is dependent upon the first. The way that changes our multiplication is that we're going to have the probability of the first event times the probability of the second event given the first occurs. So that's going to change our sample space. So let's take that deck of cards I discussed earlier. Say that without replacing, we want to draw a heart, then a spade. Now, if we know anything about cards, there are 13 hearts out of 52 total cards. So that's event A. Now when I think about event B, well, what's happened? I have now pulled out a heart, and that means there's one less card in there, but I still have all of my spades. So there are now 13 spades, but I have one less card because that single heart has been pulled out. Now that probability is very small that it's shifted, but it has gone more in favor of this pulling a spade now because there's one less heart there to do it. And now I can take my two probabilities and multiply them together. So now I can do 13 50-seconds times 13 51sts, and that'll give me about 64 thousandths or 6 4/10%. Now, say again, we want to look at the idea, what if instead of pulling a heart and a spade, I wanted to pull two hearts? So let's think through this one piece at a time. Again, step one, the event A, we pulled 13 out of 52 cards, or the hearts. Now, event B, think about how many cards are left if I've already pulled out a heart. There's only 51 cards left, but on top of that, I've pulled out a heart, so now I only have 12 hearts left. That's the distinction. So sometimes when I get that second option, that second event, it may have removed a piece as well, given that the first occurred. So now when I multiply them, I'm doing 13 50-seconds times 12 51sts, and you can see it's just a little bit less likely that I'm to pull two hearts than I was to pull a heart than a spade, because I've already taken into account that I've removed one heart. So that's about 5.9%. All right, one other aspect that's important to recognize is this notion of expected value. Now, expected value represents the weighted average outcome of an experiment over a long term. And then we often use this with gambling and with finances. So to calculate the expected value, we take the probability of winning, which we call P, and we multiply it by how much we plan to win, which is S. So we can calculate each expected value using this probability of winning times what will I win, how much will I win. And I can actually combine many expected values together if there's many different ways to win or lose at a given event. So one way that I can calculate my total expected value in a situation is to find the expected value for each individual situation and then subtract out the cost that it is to play or that it might have been to do whatever finance or game that I'm playing. So this is a great way if you are playing a game like at a carnival or some form of gambling to understand, well, what's the situation going on? So let's look at the idea of gambling. Say a gambler will win $6 if a 6 is thrown, but $60 if a 5 is thrown on a single die. However, it will cost him $20 to play each time. So how much would the gambler expect to win? So we treat each of these situations, these ways that he can win, as separate, and we add those expected values together, and then we're going to subtract out the average cost to play. So probability of us rolling a 6 is 1 out of 6 on a die, and that's $30 if the gambler wins. So that's a $5 expected value of winning on average. But you also have the idea of the 5. So the probability of rolling a 5 is also only 1/6 times the $60 of winning. So on average, the gambler would expect to win $10. Now, if I want to combine all the overall expected value of the situation, it's the probability of the first event occurring plus the probability of the second event occurring minus that cost to play. So in this case, that was $5 for if I won with a 6, $10 expected winning with a 5, minus the $20 to play on average, which would give a negative $5. Now, what does that mean? What that means is that on average, the gambler would expect to lose about $5 each time he played. So if he played 5 times, he'd expect on average that any 5 times he played, he'd lose $25. So it's that cumulative, but on average, you can expect to lose that much each time you play. Now, there's another way we can calculate expected value. So that way, the first way helps especially when you're playing games, but sometimes you may have other financial situations where it's helpful to use this method, where what I do is I take my probability of winning and I multiply it by what's the net winning. In other words, so like before we're looking at the gross winning, that's the total you win. But what if we take the net, which is how much do I plan to win minus how much it costs to play? Now I'm going to subtract, instead of just subtracting out straight out cost, what's the probability of losing times the cost to play? So it shifts a little bit of the emphasis of how the multiplication is done, but it will give you the same solution. And you can work out the algebra and see that it actually is the exact same problem, just worked out a little bit differently. So let's take this situation again. So we've got the $30 if a 6 is thrown, $60 if a 5 is thrown on the die, and $20 to play. So how much would the gambler expect to win? So instead of doing straight up the gross expected winning for each, we need to take in this idea of a net winning. So if I think about winning with the 6, I still have the 1/6 chance of winning, but now each time I win, I'm only netting $10 because I win $30, but it costs $20 to play, and that would be 10/6. Now with the 5, do the same thing again. It's a 1/6 chance of winning, but instead of winning a total of 60, I'm really only taking in $40 because it costs me $20 to play. So that's 46. Now, the last thing though is that my probability of losing. Well, if I have played and the 5 and the 6 win, that means 1, 2, 3, and 4 would make me lose. That's 4 out of my 6 options that will cause me to lose the game, and I'm losing $20 each time, which is 86. Now if I combine these all into one total expected value, just like I did before, the expected value of winning with the 6, the expected winning of a 5, minus the expected value of losing, so 10/6 plus 46 minus 86, if I work that all out, it's nice because I got a common denominator of 6, so I can add them together. I'm going to get with negative 36, which is negative 5, and again, that means on average, the gambler is expected to lose $5.